guess
Please begin, Dr. Van Diedenhoven.
Before I start, so this is the last seminar of this semester, so we'll start again in September. And we have one new person helping us out, and she allowed me to show her Facebook photo because she couldn't be here. So this is Yunha Lee. So she's on the 6th floor, if I'm correct. But 5th floor. Fifth. Oh, okay. Yeah. So yeah, if you want to give a seminar, so just talk to me or Mike or Yunha. So yeah, I want to give you a remote sensing and modeling perspective of ice crystals and deep convective clouds. And thanks to Anne and Andy for doing a lot of work.
Likewise.
So deep convective. That's it. Deep convective clouds. So I googled. I won't say it again. Cumulonimbus, and so which is deep convective cloud. But this is what you get. So there's a first Google search, and so yeah, it's all these spectacular, very big clouds that rise from the surface all the way up to the tropopause, and develop these anvils. This is a very spectacular one of Africa. So. This is a classical view of these deep convective anvil clouds. So never mind all the symbols on there, but so you have this deep convective core which rises from near the surface and shoots up all the way up to the tropopause, and can actually overshoot the tropopause some bit. So it ejects some stuff in the stratosphere. And it so if there's wind shear this way, then it develops in this way. So it develops what they call an anvil, because it looks like an anvil where you hammer on. So it develops this thick stratiform anvil piece, where there's also a lot of precipitation out. And further down, it thinnens. So after a while, you end up with very thin anvil outflow, and it can actually detach from the whole system. And it's a major driver also for thin cirrus in the tropics. So these clouds are important because their net radiative forcing. So the short wave and the long wave radiative forcing spans a very large range. So this is a figure showing the radiative forcing as a function of optical depth and cloud top temperature. So you see for very thick clouds with low cloud top temperature, you get a very negative radiative forcing. But for these thinner high clouds, you get a positive radiative forcing. And if you sum everything up in the tropics, so this is during the Asian monsoon. So this is the net cloud forcing from all these combined systems. So it ends up that it's close to zero, which is sort of a mystery why that is, because you have all these different clouds, and if you sum it up, it often ends up around zero, so no net effect. However, there's still a large range. And so the forcing in the long wave and the short wave, it depends, so like we see on clouds of temperature and optical thickness, but also on the ice crystal sizes and the ice crystal shapes, what I call, what is called habits. So when I say habits, I mean shapes. And also glaciation temperature. So it matters a lot where ice is forming, because that changes the dynamics and that changes the whole system. And there are also other things that can matter. So something about ice formation in these deep convective clouds. basically two ways to form ice. By homogeneous ice formation, so which is the direct freezing of drops, which only occurs when you get to temperatures lower than around -38 Celsius. For warmer temperatures, you can have heterogeneous ice formation, which is induced by an ice nucleus, so an IN. So Mike, when I say IN, I mean ice nucleus.
Thank you.
Where ice can form. So this happens for temperatures warmer than 38 Celsius, but so that it doesn't start at 0 degrees, but where it does start is sort of unknown, and it depends also on the ice nucleus and the environment. So you can have developing storms that still have liquid in the tops. So and if it's developing some more, you can have ice growing via heterogeneous ice formation. But you can also have at these temperatures, you could also have still liquid if you have no IN or the IN is not active. And if the storm develops very cold cloud tops, then you do form ice everywhere via homogeneous nucleation. So this is an in-situ view of the ice crystals in such a tropical deep cloud. So this is when the airplane flew through fresh anvil. So yeah, it was developed in the hour or so, I don't know. But so if you look at the photos, basically, you see a lot of what I call junk, a lot of indefined structures. This looks like a ring of plates or so, and some and think that this looks like a rabbit. But what you also see, so your eyes are focusing, are focusing mostly on the big stuff. But you see also a lot of these tiny, smaller crystals. And actually those make up most of the crystals, and most of the optical properties are defined by these smaller.
So do you see a size, morphology, distribution? Is that what you said?
Well, it's also the small stuff looks like junk, basically. But they are not as structured as these. So these look more like aggregates, and the smaller stuff looks more like more denser crystals. So this is for fresh anvil. If the anvil is more developed, then you get some water vapor growth, and you start forming these structures that look like these. So these are called bullet rosettes, which is basically one center where some arms are growing out. So it's more structures and more defined habits in these aged anvil.
Are we supposed to take anything from the 3 different columns, or is it just laid out?
So these are 3 different, it's just an example. These are 3 different storms, and these are 3 other different storms. So,
okay.
Yeah, it also varies from storm to storm. A lot of variation.
Some consistency too.
Yeah.
Well, the middle storm looks like it produces smaller stuff on average, is that right?
It could be where they are too. I don't think
Yeah,
it should be too much of this.
it depends also on the level where they are, and the temperature, and
The
everything.
closest
So
to the
it's,
source region.
yeah. Therefore, introduction, and so our objectives are, well, first of all, we want to understand ice formation better, because it's not well understood. And we use cloud resolving model studies to investigate the ice formation processes, and sensitivity to IN, and also to CCN. And we provide observational constraints on the glaciation temperatures, first of all, and also the crystal sizes and the shapes. So we use data and also modeling developed for the TWP-ICE campaign, which was near Darwin there, and in 2006, and it was sort of divided into 3 periods: an active monsoon, a suppressed monsoon, and a break monsoon. The interesting part is the active monsoon. So they started off with the active monsoon, but 4 days later everything started dying out, and it was sort of I think disappointment that they didn't get more active stuff. I focus only over ocean, where you have a very weak daily cycle. So looking at satellite overpasses over a whole period, I try to get the whole all the development stages of the storm, and I'm not so biased by having just one time overpass every day. So this is a ghost movie from during that period, TWP-ICE. So we first, it starts a little bit earlier than the 16th of January, but after a while you see it boiling up, and that's the active phase, and then you see it sort of dying out, which is the suppressed, and you see it dying out completely, which is the break monsoon. Here's Dharma.
A little bit up, yeah.
So yeah, here you see it going on. There's a lot of clouds, a lot of so red is very high, and also yellow is pretty high. So it's still boiling, and now it sort of dies out. So this is the break. There's still some things going on, but not so much. And now it turns out, turns to the so this is the break. First was the suppress. So this is the break where you don't see anything over ocean. There's something going on over land, but not over ocean. So I focus mostly on the active monsoon wave, clouds jumping up and down. So I use MODIS, which is in the A train, and I use MODIS brightness temperatures and optical thickness. And so this is a 2D histogram of clouds in different optical thickness ranges and at different temperatures. So you see these low optical thickness clouds at quite warm temperatures, and the way to interpret it, these are developing, so the optical thickness gets higher, and they're also getting to colder temperatures. And after a while, you see these very thick, very cold clouds. So these are basically the thick cores of these amber clouds. And after a while, the system sort of dies out. So the optical thickness goes lower, and but the temperature stays quite cold. And these clouds here I interpret as almost the outflow cirrus. So it's still cold, but optically thin. So the question is, so this is optical thickness and temperature. So the question is, what's ice here, and also what are the sizes of the crystals in these clouds? So size information I get from folder Parcel. I won't even try to list the full name, because it's a crazy name, and I just picked some letters in this crazy name. But but it was in the A train, so where also MODIS is. It basically ran out of fuel, so it had to lower its orbit. But yeah, for 2004 to 2009 was in the A train. Has a 10 by 10 kilometer resolution, and it measures reflectivity at 15 different angles. And it also measures polarized reflection at 3 different wavelengths. So this actually Polder is making similar measurements to what APS, which the bottom of the ocean was going to make. But APS was making it on many more angles and also many more wavelength bands. But for now, this is what we can use. This is actually in space. So it measures the Stokes vectors, so IQ and U, not the circular polarization, but it doesn't really matter in that respect. So you can define a polarized reflectance, which is basically the Q and U Stokes vectors divided by the incoming sunlight. And polarized reflectance is dominated by a low order scattering, and therefore it saturates quickly in the top of the clouds. So for optical thickness above about 2 or so, it's already saturated. So it probes the very cloud's top.
Can you give us quick intuition for what you just said about domination by low order scattering? Is that because it saturates quickly, or?
I don't really.
Single scattering is a well-defined plane. Second order scattering, you have fewer, less well-defined plane.
Ah.
By the time you get to higher order scattering, the orientation and polarization can be in almost any direction. So it's randomized simply by all different scattering angles that you're looking at through the higher order scattering.
So why is this low order?
Because single scattering, you come out with a very well-defined polarization plane, so that gives you your polarization. Higher orders, the polarization vector can be in any direction.
I understand that. So why for clouds do we see low order scattering, or why do they
For
appear?
polarization, you see low order scattering.
Does that
Because
mean
the higher orders is just
If you
randomized.
have multiple scattering, you don't see it as polarized light because they're unpolarized.
Thanks.
We probably need a whole nother slide on that.
Yeah, I think so.
Stokes
Thanks.
vector.
No time for that.
Possibly the category is memorized.
So we can use polar measurements to get information about the cloud face, and that's because so the polarized reflectance as a function of scattering angle, as you see here, you can see this very strong rainbow feature, which is very strong in polarized light. If you have droplets, you see these rainbow features. For ice, you see basically no structure. So the blue one is polar measurements above ice clouds, and this is above liquid clouds. So you already see that you can distinguish between those.
How does it know if it's an ice or not an ice cloud?
So actually, in these, I don't know how they pick the ice clouds, and maybe I don't know. Maybe there's a circular reasoning here, or maybe this is the MODIS ice clouds. But yeah, you know.
You could have
it's
just
ice
made it
clouds.
warmer than the melting temperature or
Well,
something like that.
yeah, I mean, it
Yeah.
sounds like you know that it's definitely not ice if it's above 0, that this nebulous area that you're trying to look at down to -38.
Yeah, so I don't know how they did it here, but yeah, maybe this is below -38, and the rest is above 0.
I would guess that.
But the behavior is well known
Yeah.
from lab measurements. Right?
So you can turn it the other way around, and you can use this.
So you see the rainbow in polarized light even when you wouldn't see it in visible light?
Yes,
or-
yeah. Again, because it's low order scattering, and so that the multiple scattering sort of wipes out the rainbow. So yeah, for any liquid cloud, you would see a rainbow feature. So we can use this. So we define a what we call liquid index. So which is sort of a measure of how much you see this rainbow feature in your measurements. So what I do is I take the measurements, I fit a straight line between measurements located here and located here. And so this is the dashed line here is my straight fit between measurements here and here. And I calculate basically this area, so the difference between the fit and the measurements. So if the difference is, so if there's a rainbow feature, that the difference is very big, and I get a high liquid index. So this is a liquid top cloud, 2.2 liquid index. And if I have an ice cloud, then I basically don't see a difference between a straight line and my measurements. So I get a very low liquid index. So to give a more physical interpretation of this liquid index, that's shown here. So these are simulated liquid index values for different simulations, some model simulations, and where I plot here on the x-axis the ice optical depth above the liquid part of the cloud. So I have a liquid cloud with some ice layer on top, and when it's very low optical thickness ice layer, then I end up here. And if it's a very thick ice layer, I end up here. So if you have very low optical thickness ice above your liquid layer, then your liquid index is around 3. And if you have basically an ice-topped cloud, then the liquid index is 0. So the liquid index actually tells you how much optical depth of ice you have above of your liquid part of the clouds. So what do the more ice? So what do the measurements look like? That's this. So they are binned in these optical thickness ranges. So this is during TWP-ICE active monsoon phase. So you can see that if above 0 you have high liquid index values, above 1, so you have liquid clouds. That's very good. But up to -20, still you see a quite high liquid index values. So up to -20, you still see liquid top clouds. Below, so for temperatures below -20, you start seeing these very low liquid index values. So you start seeing ice, but you also see still some liquid top clouds. And only if you go up to around -30 or so, then you start to see mostly ice top clouds. And for a colder than -40, you see only ice. So yeah, you really see these three regions. First, the liquid region, warmer than -20. This region where you have liquid or mixed or ice between -20 and around -35, and then the ice for colder temperatures. So that's the cloud phase. Another thing we can get from Polder is the information about the shape of the ice crystals. And that is because polarized reflectance of ice, of an ice cloud, depends on the shape. What you see here is global Polder measurements. So these colored contours are measurements. And the lines are for different ice models are fits, basically, model fits. And so, yeah, by doing these fits, you can sort of figure out what kind of crystals they are. But it's sort of an ill-defined problem because, well, in real life, you have all these different shapes. And also, you can, with a model, you can define all these different funny shapes. And you can, well, there's an endless possibility, of course. You can have mixtures of those. But it turns out what is the most important aspect of the model that you make is the aspect ratios of the ice crystals, or the components of the ice crystals, if you have a structure like these. So what I mean with the aspect ratio is the ratio between the maximum diameter and the minimum diameter, basically. So that's very important, and the other is the small scale roughness, and that's so you can have very pristine particles like this. So this is a plate, very pristine, but if you closely look also at the images, and if you think of how ice forms, you can have all kinds of small scale roughness on these particles. And if you model that, actually that makes a lot of that's very important.
Bubbles are a surrogate for roughness as well?
Yeah, you can also add bubbles, or you can add roughness and bubbles. It kind of does the same, has the same effect.
Of course, I want to ask about the intuition for the aspect ratio dominating the polarized reflectance. And does if you had in a lot, ice is often preferentially oriented.
Mm-hmm.
So would that have an influence?
It does. Well, you see features in your polarized reflectance due to the orientation, but it also, I mean, you see all this junk. So even if that's oriented in one way, I mean, it still has a lot of different angles to it. So if you have plates or so, then orientation is very important.
A study that was done in Polder, the orientation, they estimated when there were oriented crystals, it was less than 1% of the crystals were oriented.
So the orientation, there are different orientations because the crystals are falling through the air.
Yeah, big plates.
Does that almost mean that things are often not well-defined habits if they should be oriented, if they're well-defined habits? I don't know.
Yeah.
I think you're
I think you actually have to get quite big. I'll send you a copy of the Braille thing.
Yeah,
Oh,
Because they were looking at what the turbulent numbers had to be as against the aspect
So it
and
means they're-
size in order for
Yeah,
it
you
to
wouldn't need
orient.
much turbulence to mess up orientation. Right, let's just get things swirling around, they're not gonna just fall like this.
Yeah, so
You look at-
you have to get quite big to get a stable dishing.
Turbulence is a strong word for what might happen in a lot of cirrus, possibly, but anyway.
But on the other hand, you only need a few oriented crystals, or pristine oriented crystals to see it. So they don't have to be all oriented.
I guess sundogs are oriented, so you see them a bit now.
Yeah, you see stuff.
And what is the feature of oriented crystals in a plot like that?
Well, it's basically a specular reflection you can have. So then you see that's well, it depends on the geometry.
Any intuition on your polarization be over? Ian's question, aspect ratio, why does polarization care about
Only
aspect, aspect ratio?
most importantly.
Brian, help me out.
Sorry, Bastiaan. I'm embarrassed.
But I guess it depends on the different path of the light going through the crystal. So if you have a very long crystal, then you have a lot of paths that go basically straight through, or well, not straight through, but they have a small path through the.
Well, we're familiar with the forward scattering phase function, as a function of aspect ratio. So does it have a kind of an analog to that?
No, I can't think of a really obvious reason why the aspect ratio alone would dominate.
That's interesting.
Well, I think so. If you have a high aspect or aspect ratio close to 1, then you can have, especially if it's a little bit roughened, and you can have, it can walk around in the particle very long. But if it's flatter like this, then I think there's more chance that you leave the particle.
Even for roughness, even for small particles where you can't think about bouncing around really. If you look at prolate versus oblate spheroids, there's a structure in the phase function that marches across an angle as a function of changing aspect ratio. So the aspect ratio does control the structure of that polarized and unpolarized phase function, even for small particles. It seems somewhat similar when you look at plates and columns.
Just a little aside on this, I think I saw an HU talk around about 2003 on this data when the first folder data came in, and I think I told you this story before, but they really expected to see a lot of features, and they really didn't, and it came as a surprise. It's interesting. So what is that feature again? We do see one feature. They expected to see a lot.
It's not a rainbow? No?
No, well, it's probably
It's in one of the models.
some
It could be a
pristine.
rainbow.
It could also be rainbow, but you see here, so this is pristine
Yeah,
bullet
which one?
rosette, I think. So you do see some.
No,
It's
not bullet rosette. Is it
bit
the
of-
chain like aggregate?
It's a bit of a pity that rainbow is in the same place as these features, but rainbows. So if you really have an ice liquid cloud, then the rainbow feature is much stronger. But so it could be some residual.
So as soon as you add the distortion, it goes away too,
Yes.
basically.
Yeah.
So
Yeah.
maybe that's the main story.
So that's the next slide. So this is the sensitivity to distortion. So if these black lines are for very pristine particles, so no distortion. And then if you add distortion, you see that these features they basically go away. So so because you see hardly any features in nature, then you know that roughened ice is dominant. And this is the sensitivity to aspect ratio. So these are thin plates where you have a lot of, so the polarized reflectance is high in around scattering angles smaller than 120. And for thicker plates you have, you do see features and you have lower polarization in these scattering angles. So we can use this to get some information about the ice shape from the polar measurements. So these focus on the light gray areas here. So these are measurements of polar during TWP-ICE, and these are only for high cold clouds, so colder than -38. And overplotted are these lines. So these are for different aspect ratios. This is aspect ratio 0.7. This is 0.15. And for different distortion parameters. So what you can see here is that for these cold clouds, the best fit I get for aspect ratio 0.7, so quite compact, and roughness of 0.6, which is sort of a quite severely roughened particle. It's interesting for lower clouds, for warmer clouds, that you do see a difference in polarized reflectance. So it looks like for these warm clouds you have different shapes, different habits. And there the best fit is for these more extreme aspect ratios, over 15. But still the roughness is the same. So we got the glaciation temperature, and we got the shapes.
Actually, I just want to say really quickly that aspect ratio is really important to the symmetry parameter. I don't know if you're going to get to that.
Oh,
but something that GCM people might be really interested in.
Yeah, it's actually, so you see the asymmetry parameter of the phase function depends also on roughness and the aspect ratio. So actually that's later, actually by looking at these polarized reflectance, you can retrieve the aspect ratio of your ice particles. So now we're going on to ice sizes. So I get that MODIS retrieves the effective radius, which in this case is defined as basically the volume, the integrated volume of the ice over the integrated area of the ice. And you get that from a combination of two wavelengths. So one wavelength, so 0.8, where there's hardly any absorption due to the ice, and the 2.1 micron, where there is strong absorption due to the ice. So due to the absorption, this channel is mainly sensitive to the size, and this channel is mainly sensitive to the optical thickness. So if your measurement has a certain combination of reflectance in this channel and this channel, you end up at a point in this figure, and you can basically read off your effective radius and your optical thickness. So this is quickly how these retrievals work. So you jump straight through to the retrievals. So these are again MODIS effective radius retrievals on the left side for these different optical thickness ranges during the TWP-ICE active monsoon. And yeah, you can see that the effective radius are between around 18 to 20, 25, 28 for these cold clouds, and the retrieved effective radius is somewhat higher for these warmer clouds. I also added the 2.13 micron reflectance, where you can actually see it's a sort of a mirror image. You can see that the effective radius is this reflectance is mainly determined by the effective radius. So I'm going to use that later to evaluate the model. So talking about the model, I come here now to the model simulation. So now we know how the real cloud looks like by having these observations, and now we want to compare it to the model simulations. So it's it's DHARMA model. Some setups. It has a quite large domain. It's around 1 kilometer resolution, and it has size resolved microphysics in 36 different bins. Has two ice categories: fluffy ice and dense grapple ice. But the fluffy ice is mainly determining the effective radius and everything at the top. So I'm focusing on this fluffy stuff. And the ice properties in the model are modeled. The microphysical properties are modeled using mass diameter relationships and area diameter relationships, and also aspect ratios. So these are the same things that also govern the optical properties. So that's an interesting fact that I'll come back to later. So now I will focus on two different simulations. One, so with two different treatments of the IN. First of all, the diagnostic IN, using diagnostic IN, which basically means that you, once you form an ice crystal using an IN, you replenish the IN. So you always replenish the IN that you use up. And which is sort of unphysical, but many people use it, because actually otherwise you run out of IN, and you actually cannot model many clouds you cannot model using the other approach, which is prognostic IN, where you actually, so if an IN is used to form an ice crystal, it's used, so it's consumed by the system, and if it drains out, then you lost your IN. In these simulations, actually, you do replenish the IN a little bit, so it's nudged to the initial values on a timescale of 6 hours. So you do to make sure that you don't run off IN completely.
To account for unknown sources.
To account for unknown sources. It's a good way to say it. These simulations are for moderate monsoon event. So here you see precipitation as a function of time, and you see these peaks where you have these events coming over the. This is, I guess, is the DHARMA station. So you have these events. So it's making simulations for a strong event, also a moderate strong event. So just to show a cool movie, this is a movie of the simulation. So it's showing total water mixing ratios, and what you see is you sort of have a startup period where there's little clouds, and then you see it shooting up, and you have all these high clouds forming, and then it sort of dies out again. So there you see it shooting up, and then it kind of dies out. To show this in a different way, so these are again mixing ratios of liquid and in ice, domain averaged as a function of time. So what you see, and the red line here and here is the average domain average brightness temperature as a function of time. So you see first clouds around -20, and then it actually lowers to around 0 degrees, and then you see this development of the big system, which goes all the way up to -70 degrees. Looking at the ice, what you actually see in this first period, you see when it starts off, you start off with ice formation in close to -40, between -40 and -20. So you start off with some ice that forms, and it sort of falls down to around to around 0, where it melts. So this is what we now determined sort of a spin-off problem. So we have to cut this piece off. So we have to really focus on the big star that develops. So I cut this piece off from the simulations. I do show this because we do have some problems where we have to cut it off, or because it's sort of it's not that the spin-up ends and then you have the more interesting things develops. It sort of goes into it's a smooth transition.
Sorry, remind me, which is the one where you run out of IN? Prognostic?
Yeah, prognostic. Yeah.
And so
you do see some more ice formation also at the diagnostic line.
They're consumed but slowly nudged to the initial condition. So you would run out if you didn't nudge them at all.
Okay.
But they're consumed, so you end up being probably in most parts of it. You nudge the domain mean, so you preserve deviations from the mean. So within the cloud, you can completely consume the IN, but you're nudging the whole domain mean.
okay.
There are certainly fewer in the prognostic.
Yes, that's right. That's a good way to put it.
And that time range is only being nudged like twice
So-
or something, right?
It's a continuous.
And so the diagnostic you
So
would
it's
think
around
of
20
as being
hours,
nudged
so
with
it's
0's time scale.
4 times.
It's just,
No,
you
it's a
know, so
continuous nudge,
it's
not
instant.
Oh,
Yeah,
okay. Yeah.
okay. And that
That makes
explains
sense.
the red versus yellow?
Yeah, I mean, it's a very complex system, so if you'd asked me beforehand, will you have a way more ice right at that level? It's, yeah, it is intuitive, sure.
Okay.
But you'll delay the
Well, we could have
freezing.
explained the opposite answer too.
Like, why don't you, yeah, exactly, like, why don't you have a red spot at the top of the other one? Because you form more ice at that point, you know? So
Actually,
it's,
I think they look quite similar.
I know, at the top they do, at the
Yeah.
bottom they don't. So I couldn't have predicted that, because it's
Yeah.
so many processes happening at once.
Just to compare with the observations where you saw all these different cloud types in. So this is again the 2D histogram of the model simulations. So because it's a model simulation of this event, it's basically dominated by the thicker, higher clouds. But you do see also some lower clouds in there.
Before, when you showed this picture, you said that there's kind of a time evolution. Like, the picture you just said. This came up like 10 slides ago, right?
Yeah.
And
So
then the
these
time
are
evolution.
well,
So
it's-
that's what's missing in the second one, like as.
So, but this, of course, it sees all these different stages of systems, different systems, and so you get a sort of composite of all these systems. So yes, I interpreted this as a timeless evolution where you have developing stuff and then you have the very thick, matured anvil clouds, and then you have the dying out. And you don't see that so much in this picture because here it's basically dominated by the mature stage of the.
Polder's in the A train too, and so we used a big area with lots of different types of systems and all of that. And our main goal was to find things where you know what that cloud top of a really thick cloud, what those ice properties look like. But it's necessarily we used a lot of additional data from other conditions.
But you do, I mean, it's although you have very less clouds up here, but it is populated, so you do also, you have these different stages in the simulation also.
Is this,
Kind of.
are your objects kind of, is your simulations over the same
simulated
period or over a longer period? Your measurements?
The measurements are over a longer period, yes.
And a much wider area.
Yeah.
So
Yeah,
much
show
bigger,
that
much
figure.
bigger sample.
Yes. But so the point is, I come to that now, basically. So these are again the measurements of liquid index values. But what we have is sort of an envelope, and because we think our system is should be similar to any kind of clouds that you measure, it should at least be in the envelope. If it's out the envelope, it's different than anything you observed in this whole time period. So that's basically the way you can compare these measurements with the simulations. Speed up. I hope you can see it. IDL didn't allow me to make these symbols thicker, which is annoying. Can you see this? Can you see that?
Barely.
Yeah, that's okay. I'll talk you through it. So this is the diagnostic IN, liquid index simulations. So I forward simulated the polarized reflectance and you derive the liquid index from that, the same way as I do for the measurements. In the diagnostic IN treatment, well, I hope maybe you can see it, but there's all these points here, where it's out of the envelope. So you form a lot of ice at warm temperatures. You do also have some liquid clouds, but actually there are a few points there. Part of this can be also the spin up, but part of it is probably also if you develop the storm, you end up with too much ice in this region. Using prognostic IN, where you have less IN available, there's also, you cannot see it, but I can see it. There are some points here, but very few. So again, this could be also a spin-up problem. But what's also nice is that you do populate this area much better. So you see liquid up to temperatures around -30 or so that you also see in the measurements. So it does simulate the supercool liquid similar to the model. So this is a way to evaluate the glaciation temperatures in the model. Now look at the sizes. So again, this is the MODIS Retrievals. And it's actually, so this is effective radius. Then it's actually not as easy to use effective radius to evaluate your model ice sizes. And well, there are a bunch of reasons, but first of all, the definitions of effective radius vary, so people use different definitions. But the one I use here is basically also what you retrieve from MODIS, so stick to that. But most importantly, that most models, they don't predict effective radius, they predict masses, basically. So you have to make some assumptions to derive the effective radius from that. And you can make different assumptions, and you end up with different effective radius. So that's a problem. And also, the retrieved effective radius represents the effective radius somewhere in the top of the cloud, but where, what level is not really sure. And then also the effective radius retrievals depend on the ice habit, because the basically also the asymmetry parameter depends on ice habits. So you end up with a different reflectance in these absorbing channels if you choose a different ice habit. And finally, I want to stress that many people use the effective radius of a sphere with the same mass and use that as the effective radius of the ice. But it's because a sphere has basically the lowest area for a given mass, then you end up with a much higher effective radius than you would have for if you treat it as a real ice-shaped particle. So the way to get around this is that actually DHARMA, and so the model of N that we use, they actually in their model assumptions to calculate the microphysical properties, they already have specified first of all the maximum diameter, but also the mass and the area of the ice in these 36 bits. So this is the mass as a function of size, and this is the area as a function of size. And from the mass, just by dividing it by the density of the ice, you can get the volume. So if you use these two curves and divide them from each other, then you get the effective radius at the different size bits. So actually, but because these microphysical properties are based on the mass and the area, we can also use that to get the effective radius that the models actually model. I'm going to skip that, but this is the retrieved effective radius depends on so it represents the effective radius somewhere in the top of the cloud, but you don't know where. And past studies have shown that it sort of peaks at optical depth of 2, but it depends on a lot of things and it's very uncertain. Quickly, I want to show that the ice habit, the effective radius that you retrieve also depends on the ice habit that you assume. So again, these are these plots where you have a reflectance in the non-absorbing channel and an absorbing channel. And if you end up somewhere, a combination of these two, then you read up from this plot what your effective radius and your optical thickness is. But if you have a roughened particle instead of a pristine particle, you shift this whole thing. And also if you have different aspect ratios, you can shift the whole thing. So it depends on the habit you assume that you what the effective radius you retrieve. So we try to overcome these problems by simulating the 2.13 micron reflectance. So don't use the effective radius that's retrieved, but really simulating the measurements and compare them directly to the measurements. Because we know the ice habit, we know that the roughness, and we know the aspect ratio. So we simulate it from the model results. So that's shown here. So this is the effective radius that I also calculated. So again, I'm sorry you didn't really see it so well, but at least you see this. So it's the effective radius that I calculated. So it's the effective radius in the first two optical depths of the cloud, and compared to the retrieve effective radius. But you see that the effective radius that is modeled is slightly lower than what is retrieved, about 5 to 10 microns lower. But like I explained, there's a lot of problems with this comparison. And it's better to really look at the forward model simulations of the 2.13 reflectance, which is shown here, which are compared to the real measurements. But actually, you see a very similar thing. You see that the reflectance is overestimated, and therefore the sizes are underestimated. So this shows diagnostic ion treatment and this prognostic ion treatment, and well, there's hardly any difference, which is quite interesting. It doesn't really depend on the ion that are in place. You don't see that, but I see it. There are also some very light sizes, especially in the diagnostic ion treatment. You also see them in the prognostic ion treatment. And again, this might also be a residual of the spin-up, but it's not really known. But mostly it's too small. Finally, I want to say something about. So I formally simulate these reflectances, but like I said, I have aspect ratios closer to 1 in the cold tops and more extreme aspect ratios in the warmer tops. So to just show a sensitivity to that aspect ratio, so this is again similar to the plots I showed earlier. So you overestimate the reflectance here, so underestimate the particle size. So this is for aspect ratio of 0.7. But if I use an aspect ratio of 0.15, then I get lower reflectances, and actually they end up in the envelopes. But still, for these warmer temperature, where Polder indicates that you have these more extreme aspect ratios, you still end up with too high reflectances. So basically, the conclusion stays the same, that you have too small particles at all temperatures. So I finally come to the conclusions. So we have liquid above -20, and we have a mix between -20 and -35, and ice for colder than -40. And the shapes also depend on the temperature, and also the sizes depend roughly on temperature. And we evaluated the model by using the brightness temperatures and the reflectances and polarized reflectances. And so we do end up with some supercooled water, very cold temperatures, which is similar to the measurements. But we also see too much ice at warmer temperatures, especially in the prognostic treatment. The ice sizes are about 5 to 10 microns too small, and are not sensitive to the ion treatment in this case. And we still see some too large ice crystals in the very warm tops, which might also be a spin-up problem. And the calculated effective radius in the first two optical depths of the cloud gives a very similar conclusion as just simulating the 2.13 reflectances. So that's.
this is about your liquid index. And I would hope it isn't, but have you ever checked how sensitive the index is to water droplet size?
I didn't check it, but it's
'Cause that should affect how big the rainbow is.
yeah, but rainbow is big compared to not having rainbow.
Right, so I guess you don't care what the index is when it's above some threshold. So
Yeah. But I should, yeah. If you really wanna use it more, then I studies.
I'm skeptical that you think that this is like some unique good fit. I mean, it seems like you could have fit this one with that aspect.
Yeah, that's the point. Actually, I tried, but it doesn't really work. But yeah, maybe I should include more roughness, as I said. It doesn't. This curvature is stronger, so it sort of overshoots than here. So it's yeah. So it seems like this is